This is the second chapter, or lecture, excuse me, second lecture for Chapter 5. And starting off here, we're going to look at a term called a state function, which is a little bit confusing. We'll simply refer to it as a state function as something we don't have to worry about how we got to the end. So as long as we know where we started and where we finished, that's all that matters. And the analogy that's typically used, or I've heard several times, is like driving. So the miles on my car driving, that is not a state function. It depends which route I took to get there. So driving from Detroit to Denver, the distance that I take to get there completely depends on the route that I go. But the altitude, the elevation between Detroit and Denver, it doesn't matter which way I go. It's just my starting elevation to my final elevation. That is considered a state function, the elevation difference. Okay? So what they're mentioning here is, for example, if I have water that's at 50 degrees here, let me back up one step and change my pointer over to my marker. Try that again. There we go. If I changed my internal system here, 50 grams of water, 25 degrees Celsius, it doesn't matter how I got there, as long as I know this is the internal energy. So I could have warmed the water, or I could have cooled the water. This is my internal energy. Okay, and we'll see a couple examples of that written here, mentioning the same thing. So moving along. Something else in regards to state functions is so that internal energy, that delta E, is a state function, but the two components that go in, the heat and the work, so here we have the heat as Q and the work is W. These two things can vary going into the mix. They are not state functions, but delta E, the end result, it doesn't matter. As long as I know I started at this level and I ended at this level, these two values can vary and change, but the end result, the delta E, it doesn't matter. It's going to be the same at the end. Work, we're just going to define work as the pressure volume. So typically we'll say P delta V. So the change in the volume based on a certain amount of pressure that is going into the system. See this equation here, and we will see it again later on. So the negative sign just indicates how the system is being affected. So when the system does work, it is losing work within the system, so that's where the negative value comes from. And this is just another example of kind of going through that situation. All right, enthalpy. We've heard this last year in chemistry class. So the enthalpy of a system takes into account this pressure volume work, which we'll see here as we're moving along. And here's an equation we look at that. So enthalpy is a combination of Q, I want to say Q. E is the internal energy and this pressure volume work of the system. But we're going to change this equation around here as we're moving. So here we have the equation, and now we have the change of the system. The change in the enthalpy is the change in the internal energy, and the change in the volume based on this pressure, but we're at constant pressure. We're going to keep the system with constant pressure. But now we're going to make some substitutions into this equation. So I mentioned before we had two equations we wanted to keep track of. Internal energy is also defined as the change in the heat and the work. And then work can be defined as this equation over here. And when we put them together, something weird kind of happens is the work cancels out. So when I'm at constant pressure, the work is negligible with the constant pressure, or it's not negligible, it cancels out. So what it ends up happening is the enthalpy is equal to the energy change, or the heat change. Okay? So just looking at the term, we can say, okay, well, if the sign of enthalpy is positive, that tells us we have an endothermic reaction, which means energy is going into the system. And if the value is negative, it means energy is being lost by the system, so it's exothermic. Okay. basically saying the same thing we just went over here a second ago. Yep. Heats of reactions we'll mention here in a little more detail in just a second. Extensive property simply means it depends on the amount of material we have. So think of it, for example, a fuel, gasoline if you like. The more gasoline you have, the more enthalpy you're going to have. If you change the direction, say you want to make a fuel, you're going to have to put a lot of energy in. So energy would go into the system, which would be endothermic. But then if you ignite the fuel, energy is going to leave the system. So you can kind of see how both sides. So the sign of the system will change. For the state, we'll see this with water. You have to be specific when you're talking about the state of the energy or the substance. So the water content, if it's water in the liquid state, that is going to have a different enthalpy value as opposed if it was in the gaseous state. So you have to be specific when you're mentioning which state we're talking about. Using calorimetry, you guys probably did this last year with some ice. It's good times. We'll talk more about this probably in lecture. I found this little chart interesting just to note as far as some specific heats. And when we're talking about specific heats, we're usually referring to mass. If you want to go moles, it's usually going to be mentioned as the molar heat capacity. So in this case, take a look at the values. So we have these elements, and the ones I want to focus on would be just the metals, in which you have aluminum, iron, and mercury. They're fairly low in comparison to water. Water is a pretty special substance. Look how high the value is. So water can absorb a lot of energy or heat for every gram in every 1 degree Kelvin or Celsius. So let's listen to comparison to see. These are very good conductors, these metals, because for the amount of energy you put in, it transfers it pretty easily. For that much energy, it goes up pretty readily. Okay. Heat capacity is just that definition we kind of went over, so you can go through that. Moving along here, if we can. There we go. So this little equation here, typically there's a big C sitting here. So that would be the specific heat capacity of the system. This is the energy that's going to trade place based on the mass and the change in temperature that's going through. And you guys did a bunch of equations on that last year. Once again, our little constant pressure calorimeter. I'll move on past that. There's the equation, one form of it you may have seen before. And remember, this S is the specific heat capacity, so we'll put a big C there so you can kind of tell that. This typically we look at for water is 4.184 joules per gram per degree Celsius or Kelvin. Same thing, bomb calorimeter. Won't go into that in too much detail. Hess's law, you guys remember that. Basically with Hess's law, you can look at a reaction from its parts. So we'll see several examples of that as we're moving along. The idea is that we can do it two different ways. We can look at the different parts of the equation and flip them back and forth, and the energy will change as well, or we can look at just the end result equation. And we've done that just here. Enthalpies of formation. The idea with enthalpy formation is we're looking at a substance, say it's carbon dioxide, and if I want to look at carbon dioxide, I need to look at it as far as, okay, there's some carbon and there's some oxygen gas, and these two things will come together to make carbon dioxide. So you're making it from its elements. Alright, moving along. Slowly churning through. Okay, there we go. These are some standard enthalpies of formation. So this is the energy it takes to form these substances from their elements. So going through here, you can kind of see the various amounts. Some of these are endothermic. In other words, you have to put energy into them. And some of them, they're almost like a combustion. They're exothermic. Energy is released during their process. And some of these, for example, sugar, of course, is a food source for us and many other things. You can kind of just make some comparisons looking at some of the values. And this is just another example of how to put, using Hess's law, how to put some of these equations together to make something. So in this case, we're looking at the combustion of propane with some oxygen to produce the combustion products, carbon dioxide and water. And we can see as we're going through here, looking at the different substances that we try to obtain these values from, we don't have to include oxygen in this mix because oxygen is in its elemental form and it's the most stable form, so no energy is actually required to make oxygen from oxygen. But for propane, you have to take a look, okay, it has some carbon involved, has some hydrogen involved, and then I have to look at all these other equations making, in this case, carbon dioxide and water. And let's look at, well, actually this is a good spot to take a break because we're 11 minutes in, and we'll make another screencast here. I think we probably have one left, and we'll do that next.